left-hand side of your Schrodinger equation. So instead of writing E psi, you can write this, right? That's sort of the usual left-hand side of your Schrodinger equation. So you're substituting for E psi. So if you look on the Schrodinger equation as an eigenequation, this will be your operator, that's your eigenfunction, that's your eigenvalue, and that's your eigenfunction. Right? Remember eigenequations, right? So now this is the 3D version of the Schrodinger equation. So you got a del here, a del squared from vector calculus. Okay. All right. All right. So we have this expression here now for the average value, or the expectation value, same thing, of the energy. Okay. So here. Now for psi, we can substitute this, right? So instead of psi here, we just plug in sigma Cn psi n, and remember these now are the eigenstates for the Schrodinger equation. They're the eigenstates that correspond to a given allowed energy, right? With discrete or quantized allowed energy levels. Right? These are energy eigenstates now. Right? So so for psi star, you'll have sigma Cm star psi m star. Right? And here's your operator. And for psi, well, sigma n n n. Okay. Now just regroup terms. You've now got a double sum. Take the double sum outside the integral. These are just complex numbers. They don't change. They're just constants. So bring them outside. So you've got this, and then you're left with this. Okay. Now have a look at this. Have a look at this part here. That is the left-hand side of a Schrodinger equation. Because what is this? This wave function here is a solution to the Schrodinger equation. Right? It's when your v, the potential here, does not change with time. Right? It's a stationary, by definition, it's a stationary potential. Then this is a solution to the left-hand side of your Schrodinger equation. So you can rewrite this as En psi n, right here, because what is this? It's a solution to your Schrodinger equation. All right. So you can rewrite this here as En psi n. So do that. So now the En that's just energy. It's a scalar, right? So it's just a number. So it comes outside the integral. So you can rewrite this now as this. And here's your En that is equal to this. Well, En psi n. And so what you now, with the E coming outside, what you're left now with is the overlap integral. Integral psi m star psi n, which is rewritten is just the bracket. Okay? They're just skipping a step in a sense. Right? So the overlap integral psi star m psi n, d volume, is just the bracket. Okay. Now these are energy eigenstates assumed to be orthonormal, right? So for here, just write the Kronecker delta. Normalized. These eigenstates assumed to be orthonormal. All right. Now remember, the Kronecker delta is equal to 1 only when m and n are equal. Right. So that kills one of the sigmas. So you're just left with this, right? So one of nearly all of these drop out except when m equals n. Well, in that case, let's say m equals n. So this sigma drops out. So you're just left with sigma n, and then Cn star Cn. Well, that's just Cn squared. That's where this comes from. And En. All right. Well, that, have a look, that is this. Right? This is what we expected from statistics. If the c squared n you interpret as a probability, well, here now we've got the same expression that results from finding the average energy using solutions, these wave functions, to the Schrödinger equation. Okay? So getting the same result here confirms this idea that the c squareds here are probabilities of getting this measurement result. Follow that? You follow that logic? Okay? So pretty persuasive. Right? So it's looking increasingly like this idea of interpreting the square of these expansion coefficients, that they are to be interpreted as probabilities. Right? Probability of when you actually do the measurement, your wave function, your superposed wave function collapses to your psi k. So psi becomes psi k after the measurement, and the result of the measurement is ek. Now that's true for energy, and next chapter we will do the same kind of thing for angular momentum. So we're getting case after case for different observables, big A, that it's true. So it's looking to be like a general principle. So that's why this kind of thinking, probabilistic thinking, and c squared is the probability of getting a particular measurement, AEK, in this case it's energy, that general idea becomes so powerfully reinforced that it becomes effectively a postulate in quantum mechanics. It's one of the formal rules. It becomes, it got confirmed again and again and again so many times that it looks as though that's the way nature works. Right? That's the sort of idea. Right, now these last few lines, the usual problem, always getting cut off. So again, taking a more, so there's this same kind of example, but now we only have two eigenstates, two energy eigenstates, right? One of them is of this form, that corresponds to the ground state, and here's the next energy eigenstate, where n is 3. Remember, in this infinite square well context, your n was odd. I think n was odd. Alright? So, we can start calculating these probabilities. We can actually calculate what the values of these C's are, and hence the probabilities, and what's the probability of measuring the energy E1, the ground state energy, and what's the probability of measuring the energy E3, I think, right? But that'll have to wait for the next session. All right.